All right, problem number 6. Mr. Reed's grandparents need to make a rectangular pen for their horses. They will build the pen adjacent to a barn, and so will not require fencing along one side. Let's start to draw a diagram of this. Let's say that our barn is like this thing right here. That will be our barn. Okay, and what are we doing? We're building a pen adjacent to it, and we're saying that we're going to use the barn as part of the side of this pen area. So it's going to be something coming out like that. This is your classic river problem. So let's keep reading and label some things. It says, let W be the length of the side perpendicular to the barn. So we have a W right there, which means we also get a W right there. So we need to call that other length something. Let's just call it L for length. All right. So what do we know? We know that we have a total of 150 feet of fencing material available, and we want to know, based off of that restriction right there, what dimensions will maximize that total area. So let's go ahead and write some equations here. What is the thing we're trying to optimize? What are we trying to maximize or minimize? Well, we're trying to maximize the area. So let's write an area equation. Area of a rectangle will equal its length times its width. So that's going to be our area equation, but we want to make it more precise. And to do that, we need to think about the restraint we've been given, 150 total feet of fencing. So let's write an equation that represents the fence. So let's think about a perimeter-ish equation. Let's call it P. It's going to equal R2W plus L, because that is, those are our sides of the fence. We have one W on the bottom, one W on the top, and an L. Notice it's not 2L, because one of those sides is against the barn. But we can make this more precise. We know that the total amount of fence we have, P, is 150. So we can say 150 equals 2W plus L. So let's look at these two equations. We want to graph our area equation because that's the thing we want to maximize. And so the thing you want to maximize or minimize is going to be the equation you want to graph. But currently we have A, L, and W. So our area equation is in terms of 3 variables, and that is a problem. We need it to be in terms of just 2 variables. So we need to combine these two equations. 150 equals 2W plus L. Let's solve that for one of our variables, and then substitute into our area equation, eliminating one of those variables. I'd say the easiest equation to solve for, easiest variable to solve for is L. So let's subtract 2W from both sides. 150 minus 2W equals L. So now we have an expression for L in terms of W, which means I can take this and I can substitute it in for L in my area equation. So area equals my width times that 150 minus 2 times the width. All right, so we want to graph this equation. Keep in mind we can't graph A and W. We're going to have to graph Y equals X times 150 minus 2X. Let's make ourselves a little note. Y is area. X is width, that W. That's going to help us in a moment. So we're going to graph this, but we need to figure out what to do for our window. And to do so, we want to solve for the x-intercepts, because that's going to give us a perfect window. Notice that this x right there out front, if I plugged in 0, the entire function would equal 0. Therefore, that's telling me an x-intercept. That's telling me I have the point 0, 0. Telling me my x-min should be 0. So we want to figure out our x-max, and to do so, we're going to focus on the second factor. 150 minus 2x, we want to know when is that equal to 0, aka where does that thing give us our second x-intercept. So let's solve for x. So 2x equals 150, x equals 150 over 2. So that should be our x maximum right there. X max at 150 over 2. And you can write that as 75, or you can just plug in 150 over 2 into your window and it will do it for you. No biggie there. So once you enter your X-min and your X-max on your window, hit zoom fit and you'll get a magnificently perfect window. It'll look just like that, and you can go from there. So once it's graphed, we want to go ahead and find that maximum value up here. Keep in mind what we know. We know that has an x-intercept right there, and we found our other x-intercept right there at 75. And we know enough about quadratics to know that that maximum value right there will happen directly between those two x-intercepts. So at 75 over 2, that's going to be the value of x, aka the value of w, that maximizes this. And the question says, what dimensions of the pen will maximize the area? Well, w will have to equal 75 over 2, which should be 37.5, assuming I can do math, which is a big assumption. So if w is 37.5, we want to figure out what L is, but look, we have an expression for L right here. So 150 minus 2 times our 75 halves will equal our L. Hey look, we have a 2 and a 2, and they cancel. So we have 150 minus 75 equals L, therefore L equals 75. So the dimensions need to be L is 75, W is 37.5, and that will maximize the area. Notice it didn't ask you to find the maximum area, so you don't technically need to, and we just did this problem without a calculator, which is kind of sick. But if we wanted to find that area, remember our little key right here, Y is area. So when I calculate this maximum, second calculate maximum, left bound 0, right bound 75, it's going to tell you an x value, which is 37.5, comma, the y value, which is your area. So whatever it says, that is your area, and we are good.